Very good morning to one and all present here. I, Kajal Mishra, is here to give you a brief introduction on my topic, which is fabrication assessment of nanofiber development for wound healing. Firstly, I'll come through the content parts. The first one is the introduction, then the literature review, then the research gap, then the material and methods, then the result discussion, and the last one is the conclusion part. Let's start with the introduction. Firstly, the nanofibers have been reported to have the wide application in the field of nanotechnology. Nanofibers can be produced by using a simple, versatile, and widely applied method known as electrospinning. The morphology of the nanofiber produced can be influenced by the parameters such as applied voltage, viscosity of solution flow rate, distance of the collector from the syringe. Nanofibers obtained via this method from different polymers have proven to have potential applications in the medicine and environmental applications such as electrochemical sensors, drug delivery, and food processing. Green synthesis and fabrication of nanofibers with extract from the plant have also been explored. And recently, the electrospin nanofibers have been used as materials for wound dressing because of high oxygen porosity of the materials, and also the possession of different pore sizes, high surface to volume ratio, similar texture of natural cellular matrix in the skin, which promotes the wound healing process. Now, the applications which we are covering for the use of nanofibers are: first is the engineering and the regenerative methods, drug and therapeutic agents delivery, biological sensing, and wound dressing and antimicrobial activities. Now, the polymer nanofibers can be used either with or without any additives or in combination with the bioactive plant extract. Some of these polymers have properties such as biocompatibility and biodegradability. Biodegradable polymers could be classified into synthetic and natural polymers. Both synthetic and natural biodegradable polymers have been used for drug delivery, and some have been developed for clinical applications. The ease of transformation of some of these polymers into nanofibers has encouraged researchers to explore the possible applications available for these nanomaterials. Now, the polylactic acid falls among the list of very important polymeric material because of its easy fiber formation by electrospinning with unique material thermal stability and good solvent resistant properties. Biodegradability property of some polymers can be improved by reacting them with other biodegradable material, and the synthesis and characterization of the biodegradable composite of like PLA have been reported in literature many times. So, I can say that the plants with antioxidant antimicrobial properties have been used in the treatment of wounds. Wounds examples such as plant are aloe vera, moringa oleifera, or the ficus religiosa, and they are often delivered in the form of ointment on the affected region. And traditionally, the plant has been found the application in the pharmaceutical such as cardiac, drug and antibiotic, anti-inflammatory, antiseptic, cholesterol lowering, antioxidant, anti-diabetic, antibacterial, and antifungal drugs. And a wound is described as an injury either to the skin, underlying tissue, or organs which are caused by physical, chemical, or immunological abuse. Further, the wound is usually accompanied by, vasoconstriction, which induces homeostasis and release of inflammation mediators. And another major concerns with wound is the high risk of infection with the bacterial organisms such as S. aureus, E. coli, which are a group of bacteria that often colonizes the wound and cause infection within 48 hours. So when they are exposed. Wound healing is therefore a biochemical and physiological process of repairing the damaged tissue into its normal state. Now, these are the literature review which tells us about the use of organic extracts or like kelver or oil graphene with PLA through electrospinning fabrication process have been used for the energy generation and storage. So, another is the novel plant leaf extract with PBAT through electrospraying for the water treatment methods. A seed extract have been used with the pan polymer through electrospinning for the biomedical applications and healthcare. Another is there the use of seed oil extract with the PVA through electrospinning have been used for as has been used as a anti-cancer drug. Now, the here so reinforcing fillers which are using is the ficus religosa leaf extract, and the polymer which are using is the polylactic acid, which have been used because of the good mechanical strength, excellent resistance to chemicals and solvents, and addition to fibers. Now, here we are telling you about the how the fabrication process starts. First, mixing of the polymer solution in the plant extract and the magnetic extract have been done, and then it has been use a syringe in which we have filled the solution. After filling, there's high voltage applications on the syringe tip, and with the use of high voltage application, the first drop that comes out of the syringe, the solvent evaporates into the environment because of the high voltage, and the solid material deposit on the drum collector or the stationary plate collector, and we can peel it off and we can have a nanofiber material. Now, the nanofibers have been used for the spectroscopy and morphology characterizations, and after that for the antibacterial, antioxidant activities, and last one is the wound healing studies, which we have done on the nanofiber material. Now, first will be the FTI spectroscopic characterization of the fundamental groups present in the electrospun nanofibers of PLA only, and the leaf extract with around zero point 0.5 gram of concentration of leaf extract. Now, the spectra of PLA nanofibers only show absorption peaks at 2949 to 3014 centimeter inverse, attributed to CH bonds in CH, CH2, and CH3, while another peak at 2245 centimeter inverse is the characteristic peak confirming the presence of nitrile C triple bond N bonds and nitrile group presence in the PLA. Peaks observed at 1736 and 1198 centimeter inverse are assigned to C double bond O and CO respectively. Other peaks observed are CH stretching at 2933 and 1633 centimeter inverse due to the amide 1 and amide 2 regions. Also, the amine stretch vibrational band around 1050 centimeter inverse, and carbonyl groups like CHA stretching at 1756, confirming the presence of alcohol and carboxylic acid groups in the leaf extract present in the PLA nanofibers. Similar peaks have been observed. Uh, Similar peaks have been observed on the other concentrations of the leaf extract, which has not been shown here. Now, next is the study of SEM analysis, the morphology and TEM morphology of the PLA nanofibers, and the use of other leaf extract into the nanofiber material. So here the SEM images of all the film has been shown. Smooth, homogeneous, and bead-free nanofibers with diameter ranging from 35 to 106 nanometer were coated on PLA films, specifically those with or without use of leaf extract. However, when the leaf extract concentration was augmented, nanofibers with diameter ranging from 56 to 183 nanometer were observed, and beads were also found. Beads formation could be attributed to the decreased viscosity of nanofiber forming solutions, and caused by several compounds in the leaf extract which impeded the entangled of nanofiber. Viscosity is a crucial factor determining the structure and diameter of electrospun nanofiber. The next image is the image showing the TEM analysis of the nanofiber, and the TEM images of the prepared PLA and PLA with leaf extract electrospun nanofibers has been shown here. It has been seen that the inner diameter of prepared PLA and the leaf extract nanofibers were 602 plus minus 75 nanometer, and 415 plus minus 82 nanometer, which are in agreement with the result obtained from these SEM images. These observations clearly demonstrate the deposition of leaf extract loaded PLA nanofiber within the wall surface has been observed here. Now, next is the TGA graph, which shows the thermogrametric were employed in order to determine the weight loss pattern of the PLA and nano composite fibers as a function of temperature. As shown in figure, the TGA curve of pure PLA and the polymer nanofibers at different percentage loadings, about three-step degradation process have been identified, which are characterized by an exothermic reaction typical of PLA for both the pure polymer and the leaf loaded polymer nanofibers with different concentration. The first is the formation of rings amongst the adjacent CN functional groups in the PLA structure. This process has been reported to increase the thermal stability of the compound. The second is the decomposition of the rest fiber. In this stage, the effect of the addition of leaf extract becomes like small as a slight temperature difference between the PLA and its composite is observed. In the third stage, the residue left after the thermal decomposition showed an increment which varied linearly with the percentage of leaf extract loading. The thermal stability of nanofiber showed improvement in the high temperature region, even the lowest leaf concentration. This indicates a good interaction between the PLA and the extract. Now, next one is the wound healing. In the wound healing study, skin incision on the rat's dorsal with an area of 0.8 centimeter inverse were treated using a commercial antibacterial gauze, which is a positive control. And which is tagged with F, nanofibers which is negative control tagged with A, and nanofibers having different concentration of leaf extract incorporated and tagged with B, C, D, and E. The percentage wound closure at 1, 4, and 7, 1, 4, 7, and 10 day of treatment is shown in figure first. The histology results reveal that all the groups showed improved healing, with the wounded skin being completely regenerative at day 11. At day 1, among the rats treated with nanofiber group E showed the highest percentage wound closure among all the other rat groups. This was even higher than those treated with the commercial antibacterial gauge F. This trend was also observed at day 4 and 7. And interestingly, among the group treated with the negative control nanofiber showed some wound closure property, but not as much as those treated with the nanofiber with the leaf extract in group B to E. This is consistent with other literatures also, which have been discussed earlier. The percentage wound closure of all the groups of A to F increase gradually as the treatment time increases. Now, sorry. Now in figure next, we can see that the historical images of the wounded skin from different groups. The images of that of group A to E showed a concentration dependent healing process, as group E showed the best wound healing ability with completely regeneration as well as almost completely healed wound, and almost intact arrangement of the fibers into the dermises has been observed. As the concentration of the leaf extract content in the nanofiber increase, there is a corresponding increase in the percentage of wound closure. Now, next is the antibacterial test of the Ficus religosa leaf extract filler with the PVA. Here we can see clearly that the leaf extract have also potent inhibitory effect against the multi-drug resistant properties. The S. aureus and the E. coli have been used for the antibacterial test, and we can see that the nanofiber mat loaded with the extract B to E exhibited concentration dependent antibacterial activity against the S. aureus and E. coli. And we can see that the nanofiber mat E loaded with the leaf extract exhibited the best antibacterial property compared to the other nanofibers. The nanofiber nanofiber mat A with the leaf extract incorporated had the least antibacterial activity, and the result indicated that the extract still retained its antibacterial activity, and even enhanced activities were observed despite being processed by electrospinning. As a consequence of nanofiber B2E exhibited antibacterial activities. Now the last one in the antioxidant activity, and here also we can see clearly that the highest loaded leaf extract nanofiber, which is the orange line, showed the highest DPPH scavenging activity, and the colored have been changed completely from yellowish to the light pink into the figure. Now, in the present study, different concentration of leaf extract were incorporated uh, through electrospin mats using a electrospinning process. The fiber mats provided suitable, simple, and cost-effective materials for the wound healing and antibacterial experiments. The wound healing experiment showed the nanofibers with different concentration of leaf extract from group E to B to E gave better wound healing property compared to the uses of the only nanofiber, which is group A, which is the only polymer nanofiber, because of the presence of leaf extract with active functional group. The nanofiber with the use of polymer and the leaf extract gave the best wound healing property, which was even better than the commercial gauze. These antibacterial electrospun nanofiber mats have promising potential for the use as effective wound dressing application. So by the end, I'll thank you all for giving your attention towards my presentation, and I also want to thank Science Father and the research committee and the organizing committee to give me this opportunity to present my work in front of you all. I hope everyone had got the importance of nanotechnology and nanofibers in the field of biomedical applications. Thank you.